Hello everyone. I hope you're doing well. I hope you had a nice vacation. And to recap what we did before, we talked about backward propagation and we took examples of how we applied derivatives for backward propagation. We took like some simple examples. Then we moved forward on doing logistic regression on gradient descent with derivatives and backward propagation. So today we'll go to a small different shift, but we will apply it later on for logistic regression. Today we'll be talking about vectorization. Okay, and vectorization is basically the art of getting rid of explicit for loops. We're trying to get rid of the for loops in our code. Okay, and in the deep learning era, especially in deep learning in practice, when you want to apply it, you often find yourself training on in large amount of data. Okay, and because that's when deep learning really need to shine. So whenever you want to use deep learning in specific, you're more likely to use large amount of data. When you're working with small amount of data, you will not be really using these kind of deep learning algorithms. Okay, so it's important that your code runs quickly because otherwise, if it's trained on big data sets, your code might take way too long. Okay, and then you just find yourself waiting such a very long time to get a result. And as we spoke back in the first lecture, where with implementation we can get more speed, we can try more things. So we need to minimize the amount of time that we're working with by just simply learning new techniques, which is called vectorization. And this will help us finish way faster with if we just put normal for loops in our code. Okay, so in the deep learning era, the ability to perform vectorization has become a very key skill because it would cut so much time. So let's take a look at some examples. Okay. Okay. So what is vectorization? Vectorization in logistic regression is when you need to compute z equals w transpose x plus b. You have it here. Okay, so this is the logistic regression. Okay, this is the logistic regression that function that we have, and we're in this column we're in this column vector. We have w, and let's say we have an x column vector here. Okay, let me just get my okay. So we have here w, okay, which is a vector, and x also here, which is also another vector. Okay. So there could be very large amount of vectors if you have a lot of features. So the previous examples we took usually are DW1 or DW2. We're only taking two examples. But when you come to a neural network, you might have a lot of features. And these features are inputted in these examples, as we spoke earlier in the lectures. So W and X were both R R and X dimensional vectors. Basically, how many features that we have. Okay. So here we see the W belongs to R and X, and belongs to R and X, and R and X is the amount of features that we have. So to compute W transpose X, okay, here we had a non-vectorized implementation, which is gonna look like something like that. Okay, so z is equals to 0, and then for I in range of n to nx, okay, and that's a loop, that's the first loop. So then we'd say we update z, which is gonna be wi times xi. When we want to multiply two vectors, that's how you usually do two vectors. We're assuming if they're the same dimensions. Okay, and then you do also, because we have x plus b, you do z. You update z with the b, and b is always a constant number. So we just put it here for now. That's how the real function is actually. Okay. And then you find out that this is going to be really, really slow. However, A vectorized implementation would just compute W transpose X directly. Okay? How would this be? So, in the vectorized world, and basically when you want to implement it in Python, there's a library called NumPy. Okay? There's this command where you can use that, okay, to do a vector multiplication, which is, or if you took linear algebra, it would be called a dot function. Okay, so simply, if you do z is equals to np dot dot wx, it would multiply these two vectors together. So it computes w transpose x. Okay, this is what we have. Okay, and then you can just add b, as b is just a constant number. Okay, and you can find that this is much faster. So let's illustrate this with a little code. Okay, so here I have a little code online that it's an IPYNB file. Okay, and this is where we usually write our code. Okay, so let's take here, for example, import numpy np, and we say a is equals to np dot array. Okay, let's see, 1, 2, 3, 4, 5. Okay, if we print, it's taking a little bit time just to, you see, we have an array. Okay, so that's just it for now. Let me just take this apart. 1 second. Okay. So now that we are, so this is an example of how we can write an array in using NumPy. Okay, so here now we want to show a vectorized demo. So I'm going to import the time library. So import time, uh, and in order, sorry, and in order to time to how long to the operation is gonna take. Okay, I'm going to create an array A as well. So let's say A equals to np dot array, and let's actually take it a random np dot random dot, and it will take a million, 100,000, 1,000, a million dimensional array. Okay, we're gonna do this the same thing. So we're gonna call it B. Okay, and here we're gonna create uh, something called thick. Okay, so this can measure the current time. So say time dot time. I think this is gonna be. Let me just check for a second. Yeah, okay. So this is the current time. Yeah. And then we're gonna say C is equals to np dot ab. Okay. And talk is equals to time dot time as well. And at this point, let's print the vectorized version, which is gonna say vectorized version. Okay. Now we're gonna put 1,000 because it's the time prints it out in milliseconds. Okay, and okay, so this will show you the difference in time. Okay, let's say plus minus, because That's why we multiply by 1,000. Okay, so you can see that's how much time it took us to actually multiply a million dimensional array with each other. The reason I put a million is because uh, it it's really, if you really make it this small, okay, you will barely see the difference. So the reason is I want to make you see the difference. The bigger you do the number, okay, the more time it will take. And this is the reality. We're going to be working with, look, you can see 60 milliseconds. This is the reality of the data, that we're going to work actually with really great numbers. But we're going to take a million, for example. Okay. So now, okay, let's take an example of the non-vectorized version. Okay. Let's actually keep it in the same block of code. Let me delete this. Okay. And let's say here, C is equals to 0. Now we're writing the non-vectorized version. So, um, yeah. So we'll start with C equals to 0, just like how we explained it in the code earlier. And then we'd say that for I in range, a million, 0. Okay. We would say that C is equals plus or equal A and times B. Okay. And then we want to re-update talk equals to time dot time. Okay. And let's do a print for loop, for loop version. So here is both the non-vectorized and this is the vectorized version. Okay. Let me write this as the vectorized version. Okay. And let me show you, let me print C as well to show you that C is constant. It's the same. It's not changing. Since this is a random number, I want to show that C is constant and it's not changing. So I'll print C here and I'll print C here as well. Okay. So let's run the code. So you could see here that C is the same number that we have here. Okay. It isn't. One second. Let me check. Maybe this is not. Why is it not the same? It should be the same. The fraction is a bit smaller. It's almost a fraction smaller, but this shouldn't make a big difference. Anyways, okay, the numbers are almost the same. You can see here it's 0.00000 different. Okay, so the numbers are the same, but you can see here that the difference is almost 400 to 500 times the difference. Okay, and so that is the difference between your code taking maybe 1 minute to run versus taking around 5 hours when you're implementing deep learning algorithms. So you can really get the result back faster. It will be much faster if you vectorize your code. So you could see that if only one, even if you only had one example of for loop, this is how much difference of time it took. Okay, now again, I'm just pointing out the difference. So you can say, okay, 500 milliseconds is still a very short time, but when you're training large amount of data with a lot of for loops, these will build up, and you want your data to finish, you want your training to finish as fast as possible. Okay, so let's go back to the code. Okay, and let's go back to the slides. We talked a bit about the vectorized. Yeah, okay. So now you could see how the difference in just vectorizing your code and non-vectorizing your code would actually make a lot of difference. And this is essentially what I'm trying to show you in today's lesson, is that we need to really try to vectorize and remove as many for loops as possible, because it would really affect how fast you're running the code. Okay, and so some of you might have heard that a lot of scalable deep learning implementation are done on a GPU. Okay. But what I showed you was on a Google Colab, and which was run on CPU. So yeah, the GPU has a much better advantage of doing your computation faster. So what I just showed you, the GPU will run it even on a faster runtime than what I showed you. But still, what I'm trying to explain here is how we're trying to cut the time as much as possible. Because when you're training even on GPUs, on large data, it will take also hours, if not even days, to train your data. Okay, and we have we saw that the CPU does a fairly good job, but not as good as the GPU. And this is where a lot of companies like NVIDIA and and AMD comes to place, is where we can actually train in much faster pace. Okay, so you have seen how vectorization can significantly speed your code, and the rule of thumb is to remember, whenever possible, avoid explicit for loops. So I want you, let me put the laser. I want you to see every time you see a for loop, I want you to try as much as possible to avoid that for loop. Okay, and using explicit. Wait, hold on. Okay, now let's see more examples and start to start vectorize a logistic regression. Okay. Okay. And previously we saw examples of how vectorize is applied using built-in functions like NumPy, and avoiding explicit for loops to allow to speed up your code significantly. Now let's take a look at a few more examples. We're just gonna check a few more examples. And the rule of thumb, as I said earlier, is to keep in mind whenever you're programming a neural network and we come across uh, a for loop, we need to try to avoid this for loop as possible. Now, we're not going to always avoid the for loops, but if avoidable, we want to avoid them. And when you're programming, uh, it's not only for logistic regression, it's actually whenever possible. Okay? And it's not always possible to avoid using the for loop, but there are a lot of built-in functions where it will help you compute whatever you need. And it will often go way faster than just the regular for loop. So the point is not to see how well you code. It's trying to optimize how fast we can get those operations done. Okay, so instead of wasting your time building the logic and writing very well code, there are libraries that are helping us to compute these way faster. Okay, now let's take a look at another example. If you want to compute a vector U, okay, as a product of a matrix AV, okay, and uh, uh, and the vector and A and V are another vector, okay. Then the definition of our matrix complication is that your UI, okay, is equals to sum over a ij vj. Okay, so that's how we do matrix multiplication. Okay, that's how you define UI. And so the non-vectorized implementation of this would be set u equals np zeros. Okay, and you'd see that it is for n dimensional and one, and then for I and so on. Okay, so it would not really do it through a summation. It would just do it automatically. Okay, and here is a for loop of how we use it. Okay, so you can see we have two for loops, and that's how you compute the UI. Okay, and here we use the vectorization. This is the vectorization. Okay, so now this is for a two loop, looping over both I and j. Okay, so that the non-vectorized version implementation, which is just ui dot u a times v. So this is again, we used this earlier. The dot is just matrix multiplication. And the implementation on the right, okay, now eliminates two for loops, and it will be way, way faster. Okay, so let's go through one more example. Okay, let's say you already have a vector v in memory. Okay, and you want to apply an exponential operation on every element of this vector v. Okay, so you can put u equals a vector u is equals to e. We're making everything here exponential, as you can see. Okay, so that's e to v1, e to v2, and so on, e to the vn. Okay, so this would be a non-vectorized implementation. Let's show you the non-vectorized implementation. Okay, for I in range of n, ui will be math exponential times vi. Okay, so yes, we're using numpy expressions here. We're not really using numpy, like we're just initializing the vector of zeros, okay, to be n-dimensional rows with one column. Okay, and then we're using some functions, but we're still using a for loop. Okay, which is at first you initialize u to the vector of zeros, and then you for loop, as I told you before. And that computes the elements one at a time. Okay, so you can see here it computes u one at a time. It's going to compute this, then this, then this, then this. And this is going to take a lot of time. But it turns out that Python and NumPy have built-in functions that will allow you to compute from V to U, as you can see here. Okay, and these vectors with just a single call to a single function. So what I would do to implement this is to import NumPy as MP. Okay, and then I'll just call U is np dot exponential of v. So that would actually do what I was showing before. Okay, and so you notice that whereas previously we had to use an explicit for loop over here. Okay, here's the explicit for loop with comparing what we just have in a one-line code. So we're really making our lives really simpler. So instead of really writing longer code, we're writing one-liners, and it's even costing way, way, way less time. Okay, and here just v as an input vector. Okay, we just input v as what we would like it to be the exponential of, and u, okay, to be the output vector, because we're trying to make a new vector called u, which is exponential of everything. That's why u is the output vector. Okay, and basically the implementation on the right will be much, much faster. than the one needing an explicit for loop. And in fact, the NumPy library has many of the vector value functions. So it's really focused on machine learning and data science, and it's built really to help you compute things way much faster. So we have also, for example, if you want to do algorithmic, okay, you have np.log v, which will compute the element-wise log. And another example is the np abs, which is the absolute value. Okay. So if you want to use the absolute value of uh, every number in the vector, you would not really need to use a for loop for that. Again, when you're writing usually codes in university, things are much faster that you don't really need to realize the difference. So the code finishes really quickly. At tops, it would take like 10 seconds to finish. Okay, but when we're talking about machine learning, time is really, really crucial. And we need to cut time as much as we can. Okay, so that's why we need to use these kind of libraries. Also, one of the most commonly used is MP max, where it computes the maximum value between two elements. Here, for example, we took v and 0 and we put them into a new vector u. So that's how basically how this works is they're all zeros. And if we have v, let's say, for example, v1 is negative, then it put it as 0. And if not, it would keep the maximum number here. So this is what it basically does. Okay. And we can also have normal functions like v times 2, it is uh, being the squared of each element, and 1 over v is the inverse, and so on. Okay. So what I want you to take away from this is whenever you want to take a for loop, take a look at the NumPy library. See if there is a way to compute it using NumPy library. There's built-in functions, so you can do it without any for loop. Okay, so let's take all the learnings that we have just went through and apply it to logistic regression gradient descent implementation and see what we can get rid of, or one or two for loops that we had. Okay, so before I go to showing you the next slide, is that whenever you get on coding and you see yourself writing a for loop, my advice is check how I can check the NumPy library, see how I can remove this for loop and use something that's built in. Okay, so here is the logistic regression uh, formula. Okay, so we have done this before. Maybe you guys, it gets a bit scary every time you see it, but let me explain it a bit. Here's the z function where w is transpose w transpose x plus b is the function, and here is uh, the loss function for logistic regression. We saw this earlier, and dw1 dw2 is the features. Okay, and we saw that a minus y is also the derivative earlier on. Okay, and we saw that dw1 is 0, dw2 is 0. Okay, here we just took them zeros because we don't really care about the numbers for now. We're just taking things for example. So here in our code, to compute the derivatives for logistic regression, we have two for loops. Okay, there's one that you can see it easily, which is right over here. And the second one is actually here. Okay, so in our example, we had an x is equals to 2. Okay, we had two features. But if you had more features than just two, then we would need a for loop over dw1, okay, and dw2. Okay, so yes, right now we don't have a second for loop, but in reality, we'll never have two features. We'll have multiple features. And doing d1, d2, to nx will be hectic. So you'll need to do a for loop for this one. Okay. Uh, so it is as if there's actually for j is equals to 1 to nx to the number of features, okay, you get dwj gets updated to whatever that feature is going to be. It's going to be x nx dz, okay? So we would like to eliminate this second for loop, okay, for now. So the way we would do this is that instead of explicitly initializing dw1, dw2, and dw3, and so on, okay, they are all equals to zeros for now. So we're going to get rid of this box right now, okay, and we are going to make dw a vector, okay, an empty vector for now. So it is an n-dimensional vector with many rows and n-dimensional rows with one column, just like what we saw with u and v, okay, and they're filled with zeros, and hence the np dot zeros, okay, and this nx, okay, shows how many features that we have. So here, okay, uh, here, sorry. Okay, I'm sorry. So here we draw another box around D1 DW. I meant this one. Okay, so I'm sorry for the mispresentation. So DW, we're trying to cancel this one, okay, and loop over the individual components. Okay, so instead of going uh, DW1, DW2, DW3, and so on, we want to remove this and make a function that would go through all of the features together, okay? And that would be actually dwx equals xi dz. So again, you see here x is equals to 2, and if you had dw3, it will be x equals to 3. So this will be the iteration in which we are, okay? And it would take that derivative for that one, okay? And finally, instead of this function over here, dw1 d1 equals dw1 over m and 2 and so on, okay, we will show that it will be dw over m, okay? This is what we're gonna do only. So we still have one for loop, okay, that we have not done yet, which is this one, okay? And that loop actually iterates over all of the training examples. So this was only for one example, okay? But this for loop actually, and this goes for the features, but this for loop goes for all of the training iterations, okay? And so basically, it is for vectorization. I hope it gives you a sense of vectorization, and by getting rid of one for loop in your code, here we only removed one for loop. So we saw how in the code previously that by just changing one for loop, it could really run the code incredibly faster. But it turns out that we can do even much better. So we'll talk about vectorizing logistic regression even further. Okay, and we'll see a pretty surprising result that will really shock you, and without any for loop. So we're gonna remove this kind of for loop. Okay, and you'll see a pretty surprising results. Okay, and you could write code to express the entire training set pretty much at the same almost with negligible amount of time. Okay. But we'll go over this in a later time because I don't want to make the session too long. I'll make it in another session where it will be easier to grasp. And for now, I just wanted to introduce for you vectorization. And in the next session, the next week, we will talk how we were gonna vectorize this as well. Okay? So thank you.